Hey, Honors Physics, this is Mr. Hausman. I'm recording a quick intro to a problem that was requested by one of our students this year to get started on a circuit that is this complicated. If this is one of the choices you're going to make, we have to remember our three strategies. Okay, our first strategy is that one of the ways to start a problem like this is to color code our voltages. We're going to also use current pucks. That allows us to label where we know the current at a specific point, not just calculate it, but show it or visualize it. And then lastly, we might be using voltage tents, or we might be using a combination of all three. A voltage tent reminds us that through any resistor, there's always a drop in the voltage because there's energy that is being given off by that resistor, that light bulb, or whatever device it is. So in the first minute, all we've heard is talking strategies. Now, how do you go about narrowing down what kind of circuit you have? Well, this is a compound circuit. It has both parallel and series parts. Now, you can't see my hands as I record it, and I use this visual technique that allows you to group resistors. But I'm going to do it with parentheses. And if you were to imagine, if you could simplify this circuit, and you could look at just one part that you absolutely know is series or parallel, what you could do is you could probably start here with R1 and R3. They are very much parallel to each other, right? Because if an electron came in, it would make a division right here. It would split the current. And then, right, it would possibly split a second time. But some of the current right here, right, any current that goes through R3 has to go then to R2. So R1 and R3 are definitely parallel. So let's start with that. R1 to the negative 1 power plus R3 to the negative 1 power. And let's just call that R parallel. And I'll take out my scientific calculator. 27 to the negative 1 plus 54 to the negative 1. And I get 18 ohms. Okay, and that was parallel. So we'll write a P up there. Now, remember what we said a minute ago. If you're an electron going on this trip, anyone who goes through R1 has to go to R2. Anyone that goes through R3 has to go through R2. So what you know next is that these are series to each other. So this is R1, 3. It's the combination or the sum of R1 and 3. But then we can say, if you were to add R1, 3 to R2, you would get a series circuit. So 18 ohms added to 12 ohms, excuse me, equals a series. And 8 plus 2 is 10. That's going to give you 30 ohms. So far, so good. Excuse me. Now, if the electrons actually went that route, R1 or R3, and then R2, that's one possible route. Then we have to look out even further. What I mean by that is, what if the electrons had not gone 1 or 3? Isn't there another possibility that they go through R4? So R4 is parallel to the answer we just got for all of the part across the top line. So I'm just going to call that R4 to the negative 1 plus 30 to the negative 1. And so that's 15 to the negative 1 plus 30. And I get 10 ohms. And that's actually a parallel pathway again. So if I were to bracket this, so we've got a parallel inside a series inside a parallel. And what did we get there? I think I forgot to write it down. Parallel equals 10 ohms. Now, do you notice that R5 is tucked down here on the return path to the circuit? And couldn't it also have been drawn out here? Because basically it's the last resistor that the current flows through. So is it easier to see it out here? And then you realize that the total resistance is 10 of the parallel with this R5 added at the end, and you get a 20 ohm total resistance. Quite challenging. And then to get the current, 40 volts over 20 ohms, volts over resistance, voltage over resistance gives you current, and you get 2 amps. So the next step is where you start to use your coding system. And I'm going to erase this and keep it clean so that we can do things like we just said. We can do things like color code, or we can put in current pucks. And one of the reasons why we do that is because it unlocks the top of the table. Here's what I mean. Let's grab a new color. See how we didn't get stuck, but we finished some work and I don't know what to do next. That's how a lot of people would think about it. But I can put in the 2 amps where I know that's going to be true. It's going to be 2 amps by the battery on this side. And then it splits, but I don't know how much. And then it splits again, and I don't know how much. But by the time it comes back together, by the time it gets over here, we've got 2 amps and we've got 2 amps. And what that does is it reveals that the R5 is a great place to start after the, for the individual resistors. So let's put in 2 amps of current flowing through R5. Voltage equals I times R, so 20 volts. So that one R5 takes 20 of the 40 volts. Okay, 20 volts are dropped off here. Now let's put in some color coding. Let's use a highlighter. And remember, high voltage until you go through your first resistor. Blue, low voltage until you go through your first resistor. Now it's going to be quite complicated here, but we've got maybe a yellow here, yellow, yellow. And the reason why I picked yellow is because if I go backwards from R5, I predicted, right, that there was going to be 2 drops in the upper path, right? This part, there's going to be 2 drops here. So I had to have 3 colors. But in this path, there's really just pink to green and then green back to blue. So the color coding is not a requirement. It's just a nice skill to see. But what it hopefully helps you see is that from blue to green is a loss of 20 volts, right? Somewhere in the circuit, we're losing 20 volts at the end. And then that means then green back to red must be another how many volts? And the answer is 20 more, because the V total is equal to the V drop from maybe pink to green, or V1 plus the V drop from green to blue. So 40 minus 20 equals V1, and of course V1 equals 20 volts. So what does that mean? Who gets 20? Well, I notice that R4 is pink to green, and so that must mean R4 gets all 20 volts. I equals V over R, 20 over 15 is 4/3, or 1 1/3. And then you hit another road bump, a roadblock, maybe speed bump, and you go, well, I don't know what to do next. Well, you just calculated 1.3 amps, so let's put in a current puck and label that. And you remember a while back that we said that 2 amps goes in, right? It goes into the split. And what we just discovered is that 1.3 goes this way. So then the upper 2 paths have to get 0.7, right? Together, these two have to add up to 0.7. And then, miraculously, R2 gets 0.7 amps. Do you see what happened there? The 2 amps coming in on red, and then the 1.3 amps that went down to the bottom, not the bottom path, but the middle path that goes all the way through. 1.3 amps went through here. So then these two have to add up to 0.7, but we don't know how much. But we do know that when the current comes back together, it has to be back to 0.7 amps. V equals IR, 0.7 times 12, 8.4. And rather than finish the whole problem for you, we just are going to look at this and say, okay, anytime we got stuck with a current, Anytime we finished a current calculation, we put it in the picture. Anytime we finished with a voltage, we put it in as a tent, 20 volts. And what that allowed us to do was to figure out the next step. So usually what happens is if you can calculate one current, it leads to another current. If you calculate a velocity with Ohm's law, it leads to another velocity. These are no doubt very challenging work. I hope that gives you a head start, almost to the end, but not quite.